All right, the next big topic in this section is curve sketching. Using information that we can obtain using the first and second derivatives about critical points, increasing, decreasing, minimums and maximums, our local extrema, whether a graph is concave up, concave down, inflection points, vertical asymptotes, horizontal asymptotes, x and y intercepts. All of these are things that we can more or less calculate or at least estimate very accurately. Using all that information, we can actually accurately sketch a graph without having a calculator. So that is essentially what we're going to do. We have a curve sketching procedure here that you can look at and learn. And here we'll talk about a few things. But let's get started with an example, as it's the best way to learn. So example 4, sketch a graph that satisfies all of this information. So first thing we're going to do is go ahead and parse this information. Okay? So essentially here, what I'm seeing when I read this information about the first and second derivatives here is that there's some x values that correspond to where things switch. So it looks like the first derivative is switching its signs before and after 0, before and after 2, before and after 4. So it looks like the numbers 0, 2, and 4 are important. And if we look down here at the second derivative, the numbers 1 and 3 are important. So effectively, what I would probably do here is somehow maybe get a table going. And you can use two sign graphs to do this. I don't really care how you choose to organize your information as long as you do it in a way that is organized and it's legible. But the only way you're going to be truly successful at these problems and make it tractable is if you are organized. So I'm going to go ahead and do this table here where I'm going to put some generic intervals here. And then I'm going to talk about whether the first derivative is positive or negative, which means increasing or decreasing. So first derivative information. And then here we're going to put second derivative information, which will tell us whether we're concave up or concave down. Once we know whether the graph is, increasing and concave down, let's say, we can then identify what the shape of the graph must look like. All right. So like I said, on our number line, the numbers 0, 1, 2, 3, and 4 seem to be important because they show up here, 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 and here. So let's go ahead. So let's do to the left of 0, so negative infinity to 0, 0 to 1, 1 to 2, 2 to 3, 3 to 4, and of course after 4, so 4 to infinity. Now this is definitely a lot of information here, so this might look a little ridiculous, and that's okay for now. It's really just showing you a certain idea for now. So what do we know about between less than 0? So we know that the first derivative is, for x less than 0, the first derivative is positive. So first derivative is positive, and that means increasing. So between 0 and 1. So if, here we go, if x is between 0 and 2, so between 0 and 1, that's included here, so this would be negative. So we have negative, which would mean decreasing. And then 1 to 2 is just the second half of this, so it's still negative. So this is decreasing still. So between 2 and 3, so when x is between 2 and 4, the first derivative is positive. So for these two cells, we're going to say positive. So that's an increasing function. Increasing. So the first derivative being positive means the function f is increasing. And then lastly, when x is greater than 4, we're back down to having negative, so this is now decreasing. So now we're going to do a similar thing for the second derivative. So for the second derivative, let's start with less than 0. So if x is less than 1, so that includes when x is less than 0, we're going to have negative second derivative. So that's negative, so that would be concave down. Between 0 and 1, that is still included here, so we'd also have negative, which would be, again, concave down still. Then, for 1 to 2, so right here, this will allow us to do 1, 2, and 3, so we're going to have positive second derivative. So this will be positive, positive, so concave up, concave up. So when x is greater than 3, which also includes when x is greater than 4, we're going to have a negative second derivative. So we'll have negative, negative, which will tell us concave down. Okay. What else are we told? Well, we are told that the first derivative exists at 0, 2, and 4, and they're equal to 0. So let's go ahead here. So at 0, we're going to have a, let's just say, I'm just going to go ahead and say, well, because we're going from positive to negative, this means we're going to have a maximum. And I'm just going to go ahead and say a differentiable maximum. So in other words, something that's smoothed like this, not a sharp peak like that. This means the derivative doesn't exist. This means derivative is 0 because we have a horizontal tangent there. So we've got differentiable maximum there. And then when we go from decreasing to increasing, decreasing, increasing looks like that. So this means we have a differentiable maximum, or excuse me, a minimum. And then again, when we transition from increasing to decreasing, we know at x equals 4, the derivative exists and equals 0, so this means we have a differentiable maximum as well right there. Also here, we can think about switching from concave down to up, or up to down. So right here at this x equals 1 and x equals 3, it seems like we possibly have a point of inflection. Now, this information here doesn't say anything about what the second derivative at 1 and what the second derivative at 3 are equal to. Unlike here where they told us explicitly what the value of the first derivative is. They didn't tell us this. So we are essentially free to assume that it is equal to 0 because our goal is to draw a graph that satisfies this information, this criteria. Well, if they didn't give us that additional criteria, that means there's nothing that we have to be careful of for that. We just have to make sure that whatever we draw doesn't contradict what's already written here. So we can essentially assume that we have inflection points there and there. Okay. So now what's really nice here is if we take a circle and then think about the 4 quadrants. In this quadrant 1, we have, if we think about moving left to right, so always think about moving left to right, this would be decreasing and concave down. So this is decreasing and concave down. Quadrant 2, this would be, as we move left to right, this would be increasing, concave down. Quadrant 3 would be decreasing, concave up, and quadrant 4 would be increasing, concave up. So we can essentially use this as a little memory device to help us build what we have right in here. So increasing and concave down would look something like this. Decreasing concave down would look something like this. Increasing and concave up. Oops. I read the wrong column. Pardon me. This is supposed to say decreasing and concave up, which would be this. Increasing and concave up, which would be this. Increasing and concave down would look something like this. And lastly, decreasing and concave down would look something like this. So altogether, we can essentially draw a pretty nice graph. Let's even just forget about the axes for a second. We essentially can draw the graph by gluing these things together. So we know we're going to have first this, then we're going to have to come back around. Maybe I'll make this a little bit smaller. So there you go. And then this says we're going to, so here, maybe I'll draw this in little segments. So segment 1, segment 2, segment 3 would start like this. And then we're going to continue going up like that. And then we'll flatten out again, like that. And then we'll have that. So you have these segments that we can stitch together. So 1, 2, 3, 4, 5, 6. You can see how they all fit together. Now we just have to put our axes in the right place to make sure everything sort of fits up. So we know that this doesn't give us any information about what the y values are and everything. So I'm just going to go ahead and say our horizontal axis is like this. Okay? And now we do know that this first maximum happens at x equals 0. So that means the y-axis, the vertical axis, has to go through that point. Okay? So there we have our local max, and our tangent line is horizontal there. Our derivative is 0. So f prime of 0 is 0. So that's checked out. And I won't necessarily draw this and write this information in for all of them, but that's really sort of what you're going to visually check here and go ahead and verify. So that looks good. Then we have an inflection point at x equals 1. So right here is x equals 1, so let's just mark that as x equals 1. There's our inflection point. This is concave down. This is concave up. So here at the bottom here, it looks like we've got maybe this little dot should have been moved over slightly. That's fine. But there we have our differentiable minimum, which happens at x equals 2. So there's 2. Looks like we've got another inflection point at x equals 3. Yep, 3. And then we've got another local maximum here at x equals 4. Concave down from 3 and onward. So that is one way to organize all that information. All of these things were satisfied. So that is a graph that works out. Notice here I could have taken this entire horizontal axis, and if we shifted it up at all, that still would have worked, because they didn't give us any specific information about, like for instance, this maximum here. they didn't tell us what the y value here is. They just said f prime of 0 is 0, and we know that it is first derivative is increasing, sorry, is a positive on this side, and first derivative is negative on this side. So we knew that there had to be a max here, but they didn't say what the value of the maximum is. So this could have been lower, could have been negative, it could have been way higher up on the vertical axis. But this is a graph that satisfies that information and it doesn't contradict it.